how do we do that? That's dangerous. Well, I said, we have to find a way of doing that. Fortunately, there's some chemist that says, yeah, why not? We'll make the plumbing line of Teflon tubing all the way to my lab. Now, can you imagine? This plumbing line has to come from the foundry, which is literally, I think, the very first building back there, you know, we call it. First building, the first one there, and this building, that distance or longer. I said, no, we can't do that. I said, we have to do that. So we went back and forth, finally they succumbed. Somebody created this big pipeline of Teflon gas tubing all the way to my lab. My little tiny little lab. And we were all excited. We built our first infant device ever in the industry. So let's solve the stories. Anyway, so the story of controlling charges in MOS, there are all kinds of interesting stories, both from active and parasitic isolation device perspective. The isolation oxide needs to be significantly thicker, as we already mentioned, typically 20 times gate oxide thickness. Okay. So now you know why you make the isolation so thick, right? Simple, fundamental device physics. We'll discuss other factors, including threshold, later on. So, you know, let's keep moving. We know that we originally had those logos with bird's beak and all that kind of stuff, and we got rid of it. We have now much more elegant isolation because we knew, I mentioned those things to you. History of gate oxide charge control and reliability improvement. Gate oxide was the fun story for almost 2 decades since the FET came on board. You know, we used to have the very original FET that I built was 1,000 angstrom oxide, 1,000 angstrom. And when I directly left that doing technology, actually before that, we built some very reliable 1.5 nanometer oxide, but that's for non-volatile memory. It's no good for CMOS or field effect transistor for a different reason. That someday I will have a chance to talk to you on that. But we reliably built non-volatile memory devices with 15 angstrom interface oxide, reliably. And the technology was qualified, although we never made the product. But up to, the thinnest you can talk about oxide in any industrial sense is probably around 35 angstrom, 3.5 nanometers, simply because the transport characteristics in thicker oxides are by far not hypertonic. And anything thinner than 3, you have a band gap from silicon to the conduction band of oxide, 3.2 electron volts. So if the electrons gets energized, they can ride over the conduction line transport. And what happens is that's why, but the problem is that you go thinner, you have direct tunneling. It's a quantum mechanical particle. You have a direct tunneling. So it does not require, if the barrier is thin, below 35 angstroms or so. You have finite amount of probability to transport the charge, which sits in silicon interface, all the way to the other side. And that gives leakage. So that's why you cannot use for any real purpose as a field effect transistor, a direct field effect transistor, with any reliability when oxide is thinner than roughly 40 amps or for industrial purposes. So that's the limit of oxide. That's why, well, we knew that long before the oxide limits, so we used to make nitride in oxide for stability in thickness range. So my last, can't remember exactly, but the last technology that I directly developed for IBM, that was back in 1990, a bi-CMOS technology, where I learned about, it's the one and only bi-CMOS technology at that point. That's another story I'll tell you sometimes. But that had about, the field effect transistor had about 40 angstroms, EOT, effective oxide thickness, not exactly oxide, it's a nitride oxide. But that's about the thinnest I went before we had to go for high gate-dielectric. So, the history of gate oxide, charge control, reliability, keep the control of particulate and, all these ionic contamination that was done very beginning, as I gave you the little history. And then nitride oxide to improve the reliability of the oxides. They were used in many generations of technology further down the road. And we changed the gate, aluminum metal gate, to doped polysilicon gate for a variety of reasons that we'll talk about some other time. That was up to the LSI era. Typically, dry oxide, good, clean, dry oxide with essentially SiO2, stoichiometric SiO2 formation, is aided by higher temperature oxidation. Now there are other tricks we played, there's another story, where we could lower the temperature to make very good oxide. Why do you lower the temperature? Why do you try to lower the temperature?
So thermal budget.
Eh?
Thermal budget.
You said it. For more budget. Because everything moves, all these impurities move all around. So control the thermal budget. It's a part of integration. Is a very key factor. So, we had always since then attempted to make very clean, good oxide at lower and lower temperature. And we succeeded. So, the story of development of integrated electronics is strongly associated with oxide for many years, and still do in some fashion, but not directly as a gate insulator. Okay, important parameter for device scalability. Gate oxide, we scale the oxide, as you know, because why do you scale the oxide? Why do you scale the oxide? Why do you reduce all the charges? Why do you scale the oxide?
Sir, because we also want to scale the device, so in the same proportion oxide should be also scaled.
Precisely, because not only we scale the threshold, but we also scale the power supply. Right? Why?
To reduce the power consumption.
Exactly. We want to reduce the power. We want to reduce the power for every function. Every function we want to reduce. CV square F, remember? Yes. CV square F. Okay. We want to reduce the power, dynamic power. We want to reduce the leakage of the transistor. That means static power. Right? So it's all energy. We want to do great things, but spend very little energy, right? We can do that in our dreams, don't we? So we make the dreams into reality. Let's move on. So as I mentioned that by the turn of the century, we recognize we cannot keep on scaling the oxide anymore. So we're going to do high gate-dielectric. So I want to make sure that I have a special lecture on high gate-dielectric in one of these Friday things. All right? We'll do that. Subsequently, oxide was replaced by high gate-dielectric with lower EOT. What is the 10 nanometer technology EOT? Can anybody guess? 10 nanometer feature size, which is 100 angstroms. And now we're going into the 5 nanometer. What is the effective oxide thickness of the transistor? It's no longer oxide, but so be it. What's the EOT? You know what EOT is? It's as though whatever the dielectric is, what is the equivalent to oxide thickness? So everybody measures in terms of that kind of parameter, such that the capacitance is the same had it been an oxide of that thickness. So that's what EOT. That's all it means. It's a way of addressing thickness. So, what was my question? I forgot.
What is the thickness? EOT of that.
Oh yes. What was the EOT? What is the EOT of a 10 nanometer FET technology? Because even though I may not go into all the details to you, I want to give you the impression of what exists today. Okay. Can anybody guess? Yes, very close to it. It's 1 nanometer. It's very close to it. That's the EOT. And by the way, can anybody guess how many layers of that dielectric mix can make 10 angstrom? Just order of it, just approximately.
10 layers.
10
layers.
Sorry?
10 layers. One layer.
No.
What is the radius of?
This is a homework for all of you. Take a look at the crystallography and take a look at any of, let's say hafnium silicon oxide, or start with oxide, go to silicon oxide nitride, and then go to hafnium silicon. If I had to put a monolayer of hafnium silicon oxide nitride, just take a look at, you have to bond this, right? You have to bond silicon. What is hafnium? Silicon oxide is one hafnium atom, one silicon atom, hafnium, HFSiON. Okay? One silicon, one nitrogen, one oxygen, one hafnium. Okay, now you're bonding them. You're bonding in whatever the bond is. It could be either covalent bond or an ionic bond. One of the two. Okay, most dielectric either have the two types of bonds, ionic and covalent. Okay. So take a look at that and figure out if I have a monolayer of hafnium silicon oxide, stoichiometric means the atomic concentration of hafnium is same as silicon, as oxygen and nitrogen. So they're all like 25% atomic concentration each. So figure that out and see. If I have to create an ionic linkage, Typically, it could be 3 to 4 milliliters for a 10 angstrom. So validate that for me, please. All right. So you can see that we're talking about ULSI, we're talking about T-ox thickness, how it scales down, and now you know how it has been scaled all the way to 10 nanometer type. But this is early US LSI, and at that point we were talking about EOT of 4 or 5 nanometers. We have gone down significantly. Okay, let's go. Pad structure I mentioned already. Let's go. Keep moving. So you have a field oxide, mask oxide, pad oxide, gate oxide, tunneling oxide. This is the one I'm talking about. We use a lot for non-volatile lead. Chemical oxide from cleaning native oxide. The chemical oxide, by the way, that's interesting. I got 10 angstroms. Chemical oxide can be as large, as thick as 10 angstroms. So if you're cleaning the wafer, depending on how you clean it, you're going to end up with a chemical oxide. Because if there is a finite amount of moisture, unless you do everything in ultra high vacuum, means 10 to the minus 9 torr, where the oxygen partial pressure is extremely low,